Okay, this video we're going to look into the shear stress. We're talking about normal stress last time, sigma equal to N over A. And there's one thing I didn't mention in the last video is the sign convention. When will sigma equal to be positive? That's when this normal force is a tension, okay? When would that be negative? When we have compression, okay? So now we're going to look into this new concept called a shear. So tau is equal to V over A. So first example I want to look into is slide 23 in your PowerPoint. So which is this one right here. So there is a bar that is completely anchored into the concrete wall. And they needed to know that the total what's going to be the shear stress here, okay? So let's think about it. Shear stress have to be what? Parallel to the surface, right? Not perpendicular. So if you have this cylinder, that part of it is completely surrounded inside the wall. What is going to be the surface area look like to you? Yeah, that's going to be basically this cylinder shape, the outside of the cylinder shape, right? How do you figure out this curved cylinder shape area? I've seen this before. Remember, if you unroll it, if you cut anywhere and you unroll it, kind of like a Fruit Loop. When you unroll it, what shape does it become? It becomes a rectangle. It's like a flattened rectangle. And so for this rectangle, what would be your length here? So you unroll it. So that's basically the circumference of this circle. So that would be 2 pi r. And what's going to be the length here? That's going to be how much has been embedded to the wall. Right? If we're going to call this L here, that's L, that's a length embedded into the wall. So that's going to be L. So what you just calculated is the area, cross-section, the area where the cylinder shape that's completely anchored to the wall. That's the surface area. And be aware, this is shear V is going to be what? Parallel to the surface. So in other words, if you look at this point right here at PowerPoint, it's all those forces. It's surrounding, three-dimensionally surrounding this curved cylinder on the outside. That's going to be means parallel to the surface. Then we're going to use our formula tau is equal to V over A. And what's this internal force going to be? So now let's look at this FBD. You have this external force P pulling out towards you. And then you have this internal shear that's surrounding, only embedded to where that's anchored to the wall, surrounding the surface. All of them together is going to balance up this external force P. So all of them together are going to be equal to P. And all those forces is surrounding the cylinder surface area. That's surface area you calculated. It's 2 pi RL. That's your shear. Okay? So that's going to be your shear stress. So your internal shear divided by the cross-section area where this internal shear is parallel on the surface. Okay, so this is a very interesting concept I want you to thinking about. Why do we get this surface area and why this internal shear is equal to the external force P here. So knowing that, I'm going to look at some other examples. Jump forward to this, another example for shear. So that's slide 71. So for this one, you have a brake, AC, the top brake that's supported by two bottom break, B and D. Then there's a force acting upon the top middle section, and they want you to find what's the shear stress. Okay, so if we were trying to do FBD of this middle section here, we take it out. Then we have force going down. So you basically imagine you cut two parts, one along the AB, one along the CD. And then you will have this force is going to be supported by those two shear. Why is it shear? Because those forces is going to be parallel to this surface right here, right? Those two parallel to the surface. So each of the shears, since it's symmetrical, is going to be half of the L. Okay, and then you're going to divide it by the cross-section area. So tau is going to be equal to V over A. For this situation, the V, internal shear, since there are two of them, two equal ones, going to balance this F. So each one will be F over 2. And each of the section will be a rectangle, have B times A. That's a rectangle area. That's your shear stress. Now let's look at more example. Slide 72. For this one, those two boards are either secured by nuts and bolts or using wooden glue, as shown in C and D. And will they have the same shear? No, they're different fixture system. They're going to have a different shear. So for the first one, if you're using the nuts and screws, and you have those two forces F, they balance each other. However, if we're going to look at one board at a time, so this board, the bottom board, have this external force pulling to the right. And there must be having a force. If you're going to cut slice of the screws, there's going to be at this circle cross section, you're going to have another force going to be balance this force F. That would be your shear. And it's parallel to the circle shape. So in that situation, you have tau equal to V over A. V here is going to be equal to F. And cross-section area will be pi r squared. R is going to be the circle of that hole on that bolt. Now let's look at this scenario. If it's joined by the wooden glue, then you take the bottom plate out. The bottom plate has external force F. Then you will have another internal force that's acting upon only the contact area where the glue is on. So that's internal shear, that's equal to F. Then divided by this contact area will be B times C. Then in this formula you get the shear stress. So as you can see, they are totally different shear stress. Okay, and we call this a single shear, this entire thing, because we're about to get into double shear. Double shear is basically sandwiched. You have this bottom one is sandwiched between the two plates, one on the top and the bottom. So what will be different for this one? If you were fixed by nuts and bolt, and if you take the middle section out, and you will have top and a bottom where you slice your screws, and each of them are symmetrical. They are balanced together, this force. So now the shear is going to be half of the F. Remember in the single shear earlier slides, it's just F, but now you have two surfaces. They balance together this force, so now it's only half of F. The cross-section area is the same. It's still the circular pi r squared for the nut. Now let's look at double shear. However, is wooden joints using the glue joints. So in that situation, you also have two shear, one on the top surface, one on the mirror image at the bottom. Together, they balance this external force, so that would be F over 2 for the shear, internal shear. And for the wooden glue, this is going to be this contact area, B times C. That's going to be the double shear. Okay. So the next example I want to go over is going to be slide 75. That's our shear and normal combined. Let's look at this one. They said that this bar has square cross-section, has depth and the thickness are 40, so it's a square. The axial force is 800 Newton along the centroid axis. Determine the normal stress and the shear acting on this section AA. Also, they want you to find the normal stress and the shear at the slanted surface, BB. So that's something new, right? So now let's take a look for how do we solve a problem like this? If we were to look at our FBD, number one, when we were cutting along the AB, because if they want you to find the normal stress and shear stress at AA, we have to cut it, right? We go ahead and cut. This is where AA is. Then we obviously are looking at the left section. Now let's draw all the forces on there. We have this external force 800 kilonewton. And this is only a force, external force. So for internal, we only have N. Normal, we don't have any shear or bending moment, right? This is kind of like an axial loading. We're talking about in one video earlier. If it is just external forces along the axis, we call axial loading. There will be no internal shear, no V, no bending moment. So this will be only our internal normal force. And we calculate it, that's going to be 800 Newton. And V is equal to 0. So knowing that, we can find our sigma, our normal stress is going to be our N over area. So 800 Newton divided by 40 times 40 for the square cross-section area. And we know Newton per millimeter square give us a unit of mega. So then we will have our answer as 0.5 megapascal for normal stress. How about tau, which is our shear, right? Shear stress, this is our normal. For our shear, it's going to be V over A. There's no shear at cross-section AA, so that would be 0. There's no shear stress at all. Okay, now let's look at our second step. If we were cutting BB, which is slanted, now we're going to draw this entire different FBD number 2. So FBD number 2, that's interesting. Often when we cut it straight. But this time, we want to cut slanted. Is that important? Yes, because the shear stress and normal stress here along the BB will be different from any straight cut. As a structural engineer, you want to know at any plane, doesn't have to be perfect. It can be slanted in any angle. What will be the maximum and what's the maximum normal and shear, right? Because if that particular angle you reach the maximum, yeah, then the crack or the crash gonna along that direction. Okay, so knowing the motivation behind, now let's look at this slanted cut. We have this FBD2, and then we're gonna go ahead and label all the forces acting on there. So we look at the left section. And this left section, we still have this 800 Newton to the left. Now we have this BB. It's slanted. How do we draw the normal? The normal, remember, still have to be what? Perpendicular to that surface. So this is going to be our normal. How about our shear? Our shear have to be still parallel to the surface. And we're going to use the same sign convention to make this entire section clockwise rotation. So that will be going downward. So that's our V. And of course, we can write down our bending moment. That make it happy. But now let's look at the bending. Is bending equal to 0? If we do moment about what we cut right here. This 800 Newton going through where we cut. So 800 times 0 for moment of R. And this normal and shear both going through where we cut. So that will give us 0. And then we have this bending moment to make it counterclockwise, so plus m. So you got m equal to 0. There's no bending moment. So the only thing you need to calculate is going to be the n and v. All right, how do we figure out the n? So we do force at x direction. Force at x direction, we'll have 800 going to the left, minus 800. Then we have this normal. We're going to decompose this normal force to x direction and y direction, right? So how do we work on this? They give us this angle here. Look at this one, it's 60. So if this angle is 60, what angle will be 60 here? Okay, so this angle would be 60 degrees. Okay, you can go ahead verify it, but we have done this in statics. I'm just going to move on. This is going to be 60 degrees. If that's a 60 degrees and our x component right here, that would be what? That would be our n times sine 60 degrees, because this angle is 60 degrees as well, and that's opposite using sine. So it's n times sine 60 degrees. And it's positive since it's going to the right. That's our normal. How about our shear? Shear is this direction. That's our V. Is this V have x direction and y direction as well? Yeah, it does. So we're going to decompose this shear into x direction and y direction. Okay, so for this x direction force, and I would say this angle right here is 60 degrees. So knowing that this x direction will be it's going to be our V, right? V times, oh, I think I made a mistake. This is not 60 degrees, this is 30 degrees. Okay, how do we do that? Because this angle is 60, and so this angle will be 30, and this angle will be 30 as well. So the x direction component will be V times sine 30 degrees, because it's opposite to this angle, and it's going to the left, minus. That equals 0. Okay. Now we're going to look at the y direction. Forces at y. What do we have? We'll have this n have a y component, so that would be n times cosine 60, because it's adjacent and it's going downward, so it's negative. Then we'll decompose this shear, gonna do y component. Y component will be V. Since this angle is 30, that'd be adjacent, so V times cosine 30 and minus, that equals 0. So we got those two equations, and then we can go ahead and solve your n and v in this systematic equation. Now let's just verify our answers here. Yeah, do we get the same equations? Yeah, we do, but you might notice this, they assume the shear force going upward, so that changed the angle. So don't worry about this. If you go ahead and solve those two equations in your calculator, what would we get? We would get our N as 692.8 Newton. And with these equations, you will get V equal to negative 400 Newton. Okay, you essentially get the same answer as the slides because the V, our assumption of the direction, are the opposite at the beginning. Okay, when we get this, that's our internal normal and internal shear. What do they need to know? They want to know at BB, the slanted plane, not only know the internal normal and internal force, they want to know the stress. Okay, so we have to account for the area. So what is the area of this slanted surface? Do you think if I cut straight versus I cut slanted, do they have the same surface? No, right? If I cut straight or I cut slanted, which one will have more surface? This is a 2D because we're going to consider the depth inside. Of course, the slanted is going to have more surface area. But how much more? We're going to use the trigonometry to figure out. This is 40. And this angle is 60. So we can figure out this hypotenuse length. Hypotenuse length will be 40 divided by sine 60. Right? So let me write down the steps. So hypotenuse, we know sine 60 of a right triangle is going to be equal to opposite 40 times hypotenuse h. So h will be equal to 40 over sine 60. So that's a slanted surface length here. And be aware they all three-dimensional, the depth is 40 millimeters. So the surface area here is going to be not 40, but it's 40 divided by sine 60, which is greater than 40, right? Then the answer for this will give us 46.19. Okay, 46.19 millimeter. Then the surface area is going to be this. I'm going to erase this. This is not an area. This is my hypotenuse. Right? Hypotenuse. So the area will be this hypotenuse 46.19 times the depth, which is 40. That's my area. That is not equal to 40 times 40, right? So the surface area has increased when you have a slanted surface. So knowing that, we're ready to put everything together in the last step. So for the slanted cut, you figure out the normal, internal, and shear internal. So sigma for the normal stress is going to be N over A, and the N here is 692.8 divided by this area 46.19 times 40. And let's tag our unit. This is millimeter square, and I believe this is going to be Newton. Okay. And that answer going to give us 375 kilopascal. Make sure you pause and calculate this. Then your shear, tau, is going to be equal to V over A, and V you calculate is negative 400. But do I care about the unit at this point? I don't. I just gonna see, I don't care about the positive and negative signs. Just telling me what direction the shear force is along at that slanted surface. So it's 400 Newton divided by the same enlarged area. Then I will get 217 kilopascal. So that will be the answer for normal and shear for slanted surface. So this is a good example to showed how do we looking for internal loading for a slanted surface. So that's it. And we're done with shear stress. And we're also looking into the double shear and the single shear. Be aware those going to show up in the later problems. And we'll also look at example for slide 23 when you have a cylindrical bar that's going to be embedded or anchored to the concrete wall. What is the surface area? Think about the FOOP. When you unroll, it's basically a rectangle, so it's a circumference 2 pi r times the embedded depth, L. So that's all for today for this video, and I'll see you next time. All right, have fun. Bye.